Hi, thank you for stopping by. My name is Bach Kristensen. I'm a principal scientist at CEPharm, which is a biotech company located just outside Copenhagen in Denmark. We're part of the Servier organization, and we work as a center of excellence for antibody development within the Servier organization. Here I'll just talk briefly about how we use the different separation techniques combined with mass spectrometry in our development lab. This is an overview where you to the left here can see the different separation techniques that we now apply routinely for characterization work. Some of them are LC based and some of them are capillary based, as shown here, which is of course more relevant for this conference. We combine the separation techniques with Orbitrap mass spectrometry shown here. We have different instruments, and that's basically to support the need for the different separation techniques because it takes time to switch from one separation technique to another. So we try to dedicate the individual mass spectrometers to the different separation techniques for better efficiency. And also the data processing is of course an important aspect. All data is collected within the Chromeleon software, which acts as our data repository and also instrument control, acquisition, and simple data processing. And by that I mean when we just need to verify whether we measure a theoretical mass, if we can measure that, that is done directly in Chromeleon. But if we need to do more advanced data processing, we would use protein metric software. And by more advanced, I mean when we look at the degradation products or generally protoforms of our product. So a lot of separation techniques hyphenated to MS and processing using different software platforms. And so why is it we love intact mass especially? Well, first of all, there's no sample preparation. You just analyze the sample directly. And the modern instruments have been purpose-built for the analysis of large biomolecules. So you really get a nice spectral quality, and you also have really good sensitivity on modern instruments. Here to the right, you can see a classical mass spectrum that we get from one of our intact mass analysis. And you can see we can easily detect the non-glycosylated form of our antibody. We have forms that carry only a single glycosylation on one of the heavy chains. And then we have all the glycosylated antibodies on both heavy chains. Typically, the most abundant glycoform is the G0F, at least when you use a CHO-based expression system. And as mentioned, we can now hyphenate a whole range of separation techniques to our MS. This is very important because it allows us to characterize impurities that we detect by the different separation techniques. For instance, when we produce a GMP batch that needs to be used for a clinical development, this batch is being monitored in a QC lab. It's being release tested and stability tested in a QC lab using techniques such as size exclusion, reverse phase, or ion exchange chromatography, or imaging capillary isoelectric focusing. So with the impurity profile we see in the QC lab, we can now mirror that separation and get an MS readout directly in our characterization lab. So it really is extremely powerful that we're able to use all these separation techniques in combination with MS. And here are some examples of what the data would look like. In native size exclusion MS, by native, we simply mean that the protein is folded in it's not denatured during the analysis. And That's really nice because it's gentle conditions, and also, especially with the native SEC-MS, you combine kind of biophysical characterization where you look at aggregates and fragments if they are present. And now you can then get an MS readout and see it's more like physical chemical characterization. You can see the proteoforms combined with this separation based on size. So very nice. Ion exchange mass spectrometry. Here's another example where the black trace represents a frozen reference sample, and then we have a stability sample where we see a distinct rise in some basic forms. Typically, you would see a rise in acidic forms due to deamidation, which is common in proteins and antibodies. But here we see a distinct rise in some basic forms. And because we now have an MS readout, we can see that basic form 1 has lost 18 Dalton. Basic form 2 has lost 2 times 18. And now combining the fact that these forms are migrating basic and that they lose water, we know immediately that these are succinimide intermediates formed from aspartic acid residues. So very powerful when you combine a separation technique with an MS readout. Reverse phase MS is shown here. This is a product containing 2 antibodies. The key point here is to use difluoroacetic acid, not the conventional trifluoroacetic acid used for reverse phase separation of large biomolecules. A difluoroacetic acid gives you excellent chromatography as shown here in the UV trace and a good MS readout. And again, this combination is extremely powerful. We can see antibody 1 is identified easily, as is antibody 2. But even this minor peak in front of antibody 2, we now have an MS readout, and we can see the profile has shifted 16 Daltons relative to the main antibody 2 peak. So we know immediately that this minor peak in front represents an oxidized form. These methods have been compiled in this publication. Another example is protein AMS. So here the upstream guys simply provide us with fermentation harvest samples. So we take the fermentation harvest directly, load it into our LC-MS platform, and now we can then measure the proteoform distribution as a function of fermentation day. For this particular product, we had a quality attribute shown here, that we wanted to understand when was this attribute or quality attribute being produced in the upstream process. And the clear conclusion is that, well, this quality attribute is increasing towards the end of the fermentation process. And this is, of course, very valuable information for the upstream process guys. We can tell them that they should probably look into what's going on towards the end of the fermentation process. To the right here, we have a stacked bar chart representing the same results, and we can see that the dominating forms are, of course, the different glycoforms, but it's very interesting how we see a shift from more mature glycoforms. The orange bar here represents the G0F, G1F form, and we can see how that is dropping radically towards the end of the fermentation process. So protein AMS is really, it gives you powerful insight into the dynamics taking place during your upstream fermentation process. Now moving into capillary MS, imaging capillary isoelectric focusing can now be hyphenated to your mass spectrometer. We are using the CEInfinite from Advanced Electrophoresis Solutions. And this system can be hyphenated to any instrument, basically. Shown in the picture here, we can see we've combined it with our Explorers 480. We have the CEInfinite system here. It's basically on a mobile table, so we can roll it around in our MS lab and hook it up via a transfer capillary to the MS. And the LC, the Vanquish UHPLC, is used for the so-called makeup liquid So basically what is happening here is that you are focusing your sample in your cartridge by isoelectric focusing, and once it's focused, you acquire your image, and then the sample gets pushed out, and combined with the makeup liquid, it's pushed into the MS, where you can then get a readout. This is very important because we use ICIF extensively in QC labs, so it's one of our important impurity methods, and therefore being able to get an MS readout is really powerful. Here you can see an example of, again, a frozen reference, the black trace, and then we have a stability sample that has been stored for 4 years at 5 degrees, and it's quite a stable product. We do see a slight increase in some acidic form, which is expected because we know there will always be some deamidation as a function of time. But we also see a distinct, a minor but distinct increase in the basic form. Now, if we look at this basic form, because we now have an MS readout for the reference sample, we can see that there are 3 dominating forms in the basic peak. We have a loss of terminal glycine followed by a proline amidation on the heavy chain. That's this peak here. We then have a succinimide, which is a loss of an acidic group, and therefore it migrates basic. The mass difference between these 2 forms is only approximately 40 Dalton, so they have overlapping isotopic patterns, and that is where the high effective or high spectral resolution of the Orbitrap platform for large biomolecules really shines, because you rely on the high spectral resolution to distinguish between these very similar forms. In addition, we also see the heavy chain terminal lysine, so sometimes the cells don't trim away all the lysine, which gives you an extra basic group, hence it will migrate basic. Now, if we then look at the stability samples, we identify the same dominating form, but we now see a distinct rise in the succinimide peak. And this clearly tells us, well, the distinct rise we see in the basic form is due to an increase in succinimide in our product. And this is also kind of expected because the other variants, the terminal lysine and glylos, it tend not to be as stability indicating. They are rather quality attributes that the product is born with when you get the fermentation harvest from the upstream guys. So yeah, that was kind of a quick summary of it all. If you want to hear some more details, please watch my presentation shown here, the event. And again, thank you for stopping by.